All right, welcome back. So we are now solving gnarly integrals using complex functions and properties of complex functions in the complex plane, like the Cauchy integral formula. And what I'm going to show you now is that you can actually solve real valued integrals of a real function x, f of x, by kind of extending them into the complex plane and using these properties. So this is really cool. Sometimes there definitely are applications of this. This is pretty closely related to the inverse Laplace transform Bromwich integral. So a lot of what I'm going to show you here is going to carry over to that case. But it's also just super interesting and neat, right? This has been something people have done for a long time, is solve these really hairy real valued integrals using extensions into the complex plane. So I'm going to kind of jump in, and the example we're going to do, I actually really like this example because it gets a lot of concepts going here, is we're going to solve the integral from 0 to infinity of the function dx over x to the fourth plus, do I want to do plus a to the fourth or plus 1 to the fourth? I'm going to do plus 1. Okay, and you as a homework are going to extend this. So you are going to, as a homework, might just destroy me because I have notes here. As a homework, you are going to solve the problem dx over x to the fourth plus a to the fourth for a generic a. But it's going to make my life a lot easier on this tiny whiteboard to do this for a equals 1. Okay, so for a, I'll say, for a equals 1 is the case I'm going to derive here, but it really is totally general. It's not going to be a big deal. I might even derive it for a generic a, and then at some point when things get gnarly, I'll just say, okay, a equals 1. Okay, so be prepared for that. So this is the function we're going to solve. This is a real valued integral from 0 to infinity of a real valued function. And the first thing we're going to do, because this is an even function, it's an even function in x, we can say that this is 1/2 of the integral from negative infinity to infinity of dx over x to the fourth plus a to the fourth. And where this is going to get really interesting is that we are going to essentially, in the complex plane, let's see if I have enough space here. So this is my real axis, and this is my imaginary axis. Essentially what we have here is we are integrating along this axis from negative infinity to infinity. So the function we're trying to integrate is kind of, along this direction. And so what I'm going to do is I am going to essentially kind of create a closed orbit that includes this and a large kind of radius circle that's also going to include some poles of the complex version of this. So what we're going to do is we're going to look at the function f of z equals 1 over z to the fourth plus a to the fourth. So we're going to take this real valued function and map it into a complex valued function, where if I looked only at the real axis, it would recover my real valued function. And this complex valued function has poles at, z, so basically z to the fourth, equals minus a to the fourth, means there's poles at z equals a times the fourth roots of negative 1. And I had a lecture earlier where I showed you what all the fourth roots of negative 1 are. So if I have my complex plane and I have negative 1, and I want to know what its fourth roots are, I take its principal angle divided by 4, so that's here. And then I have kind of the 4 star points that are, 2 pi fourths apart from each other. So these are the fourth roots of negative 1. I said that pretty quickly, but I have a whole video on how to do this. So the fourth roots of negative 1, I'm assuming, are going to be things like square root of 2, plus or minus 1 plus or minus I divided by root 2. Those are these four roots of -1. And so if I have an a out front, these are the 4 poles. So these are the 4 poles of this function. A times plus or minus 1 plus or minus I over root 2. Those are the poles. And what that means is that these are poles at radius A in this star configuration. So they're going to be like here, 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 and here. They're on a unit circle of radius A. And this is pole 1, pole 2, pole 3, pole 4. And for simplicity, I'm just going to call this, A1, A2, A3, A4, where A1 is 1 plus IA over root 2. Okay, that's my definition here. And so what I'm going to do is I'm going to say that the real integral I want is essentially half of what I'm going to do is I'm going to define this large radius contour CR. And this is my integral I actually want. We'll call this like C1. The actual integral I want is this integral along the real axis. And so what we're going to do is we're going to compute. Essentially, we know this whole thing, so I'm going to do some surgery here. Please bear with me. So this plus this, we're going to call C. And this equals, so the integral of this closed contour equals the integral around C1 plus the integral around CR, okay, of my complex function. So this closed curve, where I do this whole closed curve, is equal to the real value, the integral along the real axis, plus the integral along this big radius r curve. And what I'm going to do is I'm basically going to take the limit as that radius goes to infinity, which is going to mean that this C1 becomes this -infinity to infinity integral, and this CR becomes kind of something that goes out to infinity. And I'm going to show you later that this CR, as the limit as r goes to infinity, this part of the integral becomes 0. And so this real part here is going to be whatever the contribution of these residues are to this Cauchy integral formula. So I'm going to just start solving it, and I'm going to try to recap and tie back, but we're going to use a few theorems here. We are building a closed loop that contains 2 singularities. So we're going to solve this big integral C using the Cauchy integral formula. That big integral C is going to equal the integral I want on the real axis plus this integral I don't want on this big radius as I take the limit as that radius goes to infinity. And if I show that that radius r integral goes to 0, then the integral of C1 equals whatever I get integrating this closed loop around those 2 singularities. This is going to be a bit tricky. I'm going to get into it, okay? So what I need to do first is I'm going to do this big integral C. Let me try that. And I think this is going to be kind of gnarly. So I'll be super explicit here, just real quick, one more thing. So this literally equals the integral from minus r to r of, dx over x to the 4th plus a to the 4th, plus the integral of this, radius r curve, dz over z to the 4th plus a to the 4th. This thing equals a closed contour around C of dz over z to the 4th plus a to the 4th. And I'm going to take the limit as r goes to infinity, so this becomes -infinity to infinity, the thing I want, and this is going to go to 0, so I just need to compute this thing. Okay? Whew, all right. And this is going to be true for any closed contour that contains these 2 points for any radius that's big enough, that's bigger than a. So for radius 1, 10, or 1,000,000, or the limit as r goes to infinity, this actually isn't going to change because of this Cauchy integral formula. So how do I do this? I think the key property here is that this is equal to the integral around this closed contour I can factor this z to the fourth plus a to the fourth. This is z minus a1 times z minus a2 times z minus a3 times z minus a4 dz. And away from a1, all of this other part of this function, I'm sorry, that was a mess. This is a z. Away from a1, all of the other terms in this expression are analytic are analytic at a1. This is the only part of this function that's not analytic at a1. Similarly, around a2, 1 over z minus a1 times z minus a3 times z minus a4, that's analytic at a2. The only part that's not analytic at a2 is this part here. So we can use the Cauchy integral formula to essentially say, I'm just going to start writing this down and hope that's pretty close to right. This is going to be, I'm going to kind of shrink wrap this around each of these and write this as two different pieces. This is going to be equal to an integral around this one and an integral around this one. I'll call this CA1 and CA2. So this is the integral of CA1 of the analytic part of my function, which is 1 over z minus a2 times z minus a3 times z minus a4 over z minus a2. And again, using this Cauchy integral formula, oh, crud, this is a1. I probably shouldn't do complex analysis for 6 hours straight. Z minus a1. So this is one part. This is the integral around CA1 dz plus the integral around CA2 of the part that's analytic, which again is 1 over z minus a1 times z minus a3 times z minus a4, all of that over z minus a2 dz. Let me just recap here. I've taken this big contour integral, and again, I can continuously deform that so that it's basically hugging these two singularities, maybe with a tiny little connector between them that's going to cancel out. And so this is, this big integral around this closed loop is equal to the shrink-wrapped integral around this one plus the shrink-wrapped integral around this one, because Cauchy-Goursat says I can deform these continuously until I hit a singularity. And so the integral around this a1 point, I'm claiming that of this big gnarly function, 1 over z to the fourth plus a to the fourth, this part of the function is analytic at a1, and this is the only part that's not analytic. So we've broken this down into something that's analytic divided by z minus a, and then for the second singularity, similarly, these three parts of the denominator are analytic. So this is the analytic part, and this is the singular part. And so by Cauchy-Goursat, this is pretty cool actually. This whole thing is 2 pi I times this whole numerator part evaluated at a1. So times 1 over a1 minus a2 times a1 minus a3 times a1 minus a4. Now, this looks like a mess, but each of these a's are actual complex numbers. You can plug in a1 and a2 and a1 and a3 and a1 and a4, and you can chug this through on a big old piece of graph paper, and you'll get a number, a complex number out. So this is basically solved. This is done. This is a number. We can compute this pretty easily. I don't want to do it, but we could do it. Similarly here, because of the Cauchy integral formula, this being the analytic part here, and this being the singular part, is 2 pi I times this analytic part evaluated at the singular value. So plus 2 pi I, and only a little bit changes here. Now it's a2 minus a1 times a2 minus a3 times a2 minus a4. And again, I can kind of chug through and compute these, and I have done it here. And so I'm just going to leave this as an exercise. You can download this PDF and see like the nitty gritty carry the root 2's and all that crap. It doesn't matter. What this equals is essentially I get 2 pi I divided by 2 root 2a cubed I, which simplifies to pi over root 2a cubed. Okay, all you have to do is plug in a1, a2, a3, a4 into these expressions and do do the math with these a's, and this is what's going to pop out. Okay, this is the integral around this closed contour for any radius r that includes these 2 points. For any radius bigger than this than the radius a, for any r bigger than a, this integral equals this. So now all I have to show is that if I take the limit as r goes to infinity, this term goes to 0, then the integral I care about equals this expression here. So the last thing I have to do is show that this integral goes to 0 as r goes to infinity. Okay, I hope you're with me. And in that case, what we will have is that this will equal this, which means that the integral I care about will be 1/2 of this. Okay, so that's what we're going to show, is that the integral I care about, this integral here, is going to be 1/2 of this if this other half, this circular half, goes to 0 as my radius goes to infinity. I'm going to erase a bunch of stuff, so I am going to count on you to remember, or you can always pause or go back and find this board later. I'm going to erase most of this stuff, and we're just going to show that this integral goes to 0. Okay, so maybe here's what I'll do, is I'll keep the punchline of this right here. So this equals pi over root 2a cubed. And I'm going to erase all of this stuff, and then we're going to show this last term equals 0. So, okay, the last thing I need to show you now is that this big radius part of my closed contour C goes to 0 as r goes to infinity. And we are going to do that using the ML bound that I showed you earlier. It's a very intuitive property. So we're going to show that the limit as r goes to infinity of the CR portion of dz over z to the 4th plus a to the 4th is going to equal 0. And the way I'm going to do that, how do I want to do that, is essentially using the ML bound. So I'm going to show that the integral around CR of dz over z to the 4th plus a to the 4th is going to be less than or equal, the norm of this is going to be less than or equal to m times L, where L is the length of this curve, which is pi r. Okay, pi r is the length of this curve. So this is pi r. And m is going to be kind of the max value of the function on this radius, which I'm going to claim is going to be something like 1 over r to the 4th. So it's going to decay way faster than r grows. So clearly the length equals pi r, and m equals the max over CR of 1 over z to the 4th plus a to the 4th, which is less than or equal to 1 over r to the 4th. Clearly a is positive, so this can only be worse than 1 over r to the 4th. And so m is 1 over r to the 4th, which means that this thing is less than or equal to pi over r to the 3rd. And as we take the limit as r goes to infinity, this integral becomes 0. This integral gets smaller and smaller as I push that radius out to infinity. So this entire term here, this entire term goes to 0 as r goes to infinity. And similarly, as r goes to infinity, this term equals twice the value of the integral I want. So the integral I want here equals this quantity divided by 2. Okay, sorry, that is like completely illegible. This integral that I want equals this quantity divided by 2. Okay, this is, I'm not gonna do a super recap on this. This had a lot of pieces. This synthesized all of the integral theorems we learned in complex so far. We used Cauchy-Goursat to deform our contours, in regions where they're analytic. We used the ML bound to kill this big radius part as we took the limit as r goes to infinity. We used Cauchy integral formula to solve for the closed contour surrounding 2 singular points using this Cauchy integral formula by computing kind of the 2 residues and adding them up. And we solved for this half domain real valued function by the fact that it's even, extending it to an infinite real integral in this framework. Pretty cool stuff. This is actually very, very similar to what we're going to do in inverse Laplace transform, where now what we're going to be doing is trying to integrate along a contour that goes kind of from minus I infinity to plus I infinity, and we're going to create this big Bromwich integral, and we're going to integrate around singular points, and we're going to do something very similar, kind of knocked over on its side. That's how we're going to do the inverse Laplace transform using the Bromwich integral. All right, stay tuned. Thank you.